Hi students. So we are going to begin optimization tutorial 15. Today I'm going to talk about the Fletcher Reeves method. This is one of the popular conjugate gradient methods. I'm Dr. Ganguly. Now in today's video we are going to discuss the Fletcher Reeves method. Now we are going to write Python code to solve this problem. Because what happens is that as far as these algorithms are concerned, the best way to figure them out is to actually write code to implement the algorithm. The math and the theory, if you are interested in that, and you should of course take a look at that, you can take a look at optimization lecture 15 on the conjugate gradient method, and of course do see my optimization playlist for the full course. Now the direct search methods in optimization can be given by this expression here in blue, that is xk plus 1 equals xk plus alpha k dk. And this vector dk, the search direction, this essentially comes from different methods out there. These are algorithms which have been proposed by various researchers across the past decades. So let us look at the conjugate gradient method in terms of dk, and this is the Fletcher Reeves method. There are several conjugate gradient methods. We are going to discuss them in later tutorials. So as far as Fletcher Reeves is concerned, they propose that dk is minus ck plus beta k into dk minus 1. So in this case, you see that this method has some aspect of bringing information from the previous point, that is k minus 1, into the current point. And if you think of this method, it actually retains the history of all the previous methods, because you are going to continuously keep the previous value, and so that's going to come into the current search direction. Now beta k here is defined as this ratio, so it's the norm of ck divided by the norm of ck minus 1 square. So essentially we are going to write a program to implement this method and see how it compares with the steepest descent method, or the gradient based optimization method, which we discussed in, I think, optimization tutorial 13. So now if you look at the Fletcher Reeves method carefully, you will see that you need dk minus 1 and you need ck minus 1. So when you are starting off this algorithm, you actually do not have the k minus 1 point. For example, if you are at k is 0, you are not going to have the point before that. So what we do is that when we start this method, we use the gradient descent or steepest descent search direction, which is simply d0 is minus c0. So this is the steepest descent search direction. You remember there we simply say that d is negative c, and so we are doing that at k is 0 here. Of course, you need x0 to be given. You need the starting point to start off these gradient based methods. And then you proceed forward in this manner. Xk plus 1 is xk plus alpha k dk. Remember, alpha k is the one-dimensional step size. We need to calculate this using some algorithm, one of the 1D search algorithms. And then we of course find dk using this formula here. So now let's try to implement this method in Python code. So let's frame this first question here, which is write a Python program for the Fletcher Reeves method. And also we are told to use 1D search and then find the minimum value of this function, which we have been using as a test function in this course. So the function is x1 square plus 2x2 square plus e to the power minus x1 minus x2, and the starting point x0 is given as 1 and 0. So this is a two-dimensional multivariate function minimization problem, unconstrained of course. So let us start with the function itself and the gradient vector. So of course you see the function is x1 square plus 2x2 square plus e to the power minus x1 minus x2. So we can write it in this form here. So here you clearly see that we have defined this term here, which is the exponential term, and I simply add this term to x1 square plus 2x2 square. Now remember, of course, in Python, vectors start from x0. So x1 becomes x0, x2 becomes x1. So keep that in your mind. There is a difference when you convert math to Python. Now the gradient vector is given as follows. So we can code it here. This is of course a vector. So we have to bring in np here, that is numpy. And then we define the first term and the second term of this vector. So the first term is going to be 2 into x1 minus this exponential term, and the second term is going to be 4 into x2 minus the exponential term. And of course, I have another function here. This function is required in the one-dimensional search. So essentially, let us assume that at some point I have xk, I have dk, and I put in some value of alpha. So then I essentially can get this point. I can calculate the function value at x plus alpha into d, and so that's going to give me the value for that particular alpha here. So essentially this function f1d, this invokes the function f here, and it returns the value at x plus alpha d. Let us now write the main program first, and then we are going to delve into the Fletcher Reeves function, which is going to do all the Fletcher Reeves descent, search direction, and so on. So essentially, I of course first import numpy as np. I declare the starting point x0 as 1 and 0, like it's mentioned here in the math. And then I create two small numbers. One is tolerance, is 0.000, or I should say 401. This is a small number. And the second number is a relatively large number. This is used for the for loop. So essentially I loop up to 1,000 times, but most of the time I don't have to loop that much. I essentially put a break statement to break out of the for loop. So this essentially represents the for loops in both the cases for the 1D search and the Fletcher Reeves. Then I have defined this Fletcher Reeves function here. This is going to take x0, that is the starting point, the tolerance value, the small number, the max value, the large number, and it's going to return to me x star, which is the minimum point for the function, and k being the number of times it took for this particular k value to converge. So essentially maximum is 1,000, but generally we will see it converges in a few values of k. And then I print out Fletcher Reeves results. I print out the minimum point. This \n simply creates a new line. It lets me have a better output. Let's now write the Fletcher Reeves function here. So I again start with x is x0, and I have this for loop here. The for loop is from I in range max. First thing I do is I put the gradient of f x in C, and then I have two parts of this if statement. If I is 0, I simply put d is minus c. Remember, that's the steepest descent search direction. But after I has become greater than 0, I actually put the conjugate gradient direction. So in that case, I first calculate beta. Beta is going to be this divided by this, which I do here. Now I don't need to square this because I'm simply taking the dot product, so it's squared by itself. And then I put d is minus c plus beta into d old. So this is this value here. Now essentially what happens is that I calculate this d old, or rather I put this d old here as d from the current point, and I also put c cold is c. So these are the old values, so that is c old and d old, which I am putting here, and I am using this c old here, that is ck minus 1, and I am using d old, that is dk minus 1. Then I of course print out various values. I print out the step size, that is alpha, I print out beta, and so on. Now at this point I actually call the one-dimensional search here, and in the one-dimensional search what goes in is of course d and x, which have been calculated here. D is calculated here, x is coming in, and of course the same tolerance and max I am using here also. I'm using the same value in the 1D search and in this particular loop to reduce the number of variables. But of course you can create different variables and have a different level of convergence in the one-dimensional search and a different level of convergence in the problem here. Now here I actually break out of this for loop if the norm of the gradient vector becomes less than tolerance. So that's the criteria here. Remember, the necessary condition for a function being minimum is that the gradient should be 0. So numerically we say that the norm of the gradient should be below some tolerance value, and I have put the tolerance value to 0.00001. Now if that happens, then I break out and I return xi, or I simply keep going through this loop until this point happens. Now we have discussed this function before when I looked at the steepest descent method, But again, let us just review it. So essentially I start off with alpha is 0 and I keep a delta value of 0.05, n is 1000, and I put a star is 0.1, and then I loop through this problem here. I have a for loop, and what I do is that as long as I is greater than tolerance, I start with I is 1, but I is going to shrink because I is going to be the bounds I have got. I keep doing this thing here. Now what happens here is that I take a lower value of alpha, I take a middle value, I take a maximum value, and then I try to locate the point at which the minimum has just been crossed. And at that particular point I essentially stop. I declare a star is half of the alpha low and alpha upper bound. I is the difference between these two, and of course I set alpha as the lower bound here, so that's important. And of course I divide delta by 10. So what I do is I create a finer mesh for the next round of this loop here. So I keep doing this, and what's going to happen is that at a certain point I'm going to break out of this loop, and once I break out of this loop I return a star, and then I return a star from this problem. So essentially this particular function, what it is going to do, at the end of the day it is going to give me the alpha value, or rather I should say alpha star value, given I have input to it d and x. So it's going to go through various values and it's going to give me the optimal or the best value. Let's run the code. So I run it at x0 is 10, so that's the starting point. You see I get the starting point here. So it has calculated a step size of 0.42. First round beta is 0. Then I have one more point here, step size is given here, and so on. Beta values are given here. And then very quickly I have converged to the Fletcher Reeves output, which is very close or almost same as the one I got from closed form solution. Remember optimization tutorial 3, where we got this exact solution by setting the gradient vector to 0 and solving that equation. That equation had resulted in Lambert W function. If you are not familiar with that, check out optimization tutorial 3 at the end of this lecture. Now let's look at some more things. Now whenever you have a code, actually one of the advantages is that you can do a lot of numerical experiments to check out the algorithm. That's one of the main purposes of actually writing a code. And that is the reason why knowing the math is not sufficient. You actually need to know programming if you are ever going to do scientific computing or numerical computing. So now let's use this Python code on the same function, but we are going to start with 0, 0, 5 minus 5 and 0.31, 0.15. Now you can see that one of these solutions is very close to the actual minimum point and the remaining two solutions are somewhat far away. In case we know nothing about the problem, we can always start with this kind of vector such as 0, 0. Now if you have an n-dimensional problem, you would simply use n zeros here. Let's start with this solution here. This is a situation where you know nothing about a preliminary design or a particular solution of this problem. So we have put 0, 0 here, and then we have run the Fletcher Reeves method. So I converge here pretty quickly. You see how nicely it goes from 0, 0 to certain values, and then the values keep changing until we have converged to the actual minimum point given here. So pretty quick convergence. So here I is 0 and by 4 you have converged. Let's try a solution which is very close to the actual optimal point, and we have put that here 0.31, 0.15. Let's run it. You see this converges in just one shot. So essentially I get the solution as 0.3127 and 0.1563. Of course, you know that in these kind of numerical methods which are based on gradients and calculus, the point is that you are going to converge very quickly if you already know the answer. So that's the case in some cases, but in most cases it's not. Now let's start with a point which is pretty far off. So I have taken 5 and -5. So this is not only quite far off in the sense of the magnitude of the problem, but you can see for the second coordinate here, that is x2, the direction is also off. So it is in a negative direction. So I put that here 5 minus 5, and then we run this code here. So in this case, it takes slightly more time, but by I is 5 here, you have converged. So it's interesting that very quickly you actually go from 5 minus 5 to both positive numbers, and then we are quickly converging here. Now, of course, the step size is being calculated pretty much exactly here, or I would say quite accurately, because I have specified a 5-digit tolerance as far as the 1D search is also concerned, and you can see the beta values here. These are the beta values which are typically trademark and standard for the Fletcher Reeves problem. Remember, in this problem what's happening is that the gradient vector is being slightly deflected by using this beta value and the previous search direction. Let's now do one more problem, and here what we are going to do is compare the Fletcher Reeves method with the gradient descent method and see how much time, or rather how many runs does both cases take to converge. So again, same function, but let's start with a point which is pretty far away to see how these methods do. So here what I have done, here is the main program. Here I made some slight changes because actually I have cleaned up somewhat the argument list of both steepest and Fletcher here. So I got these here. I start off with -5 and 5, and again same tolerance and max, and then I print out steepest descent and Fletcher Reeves. So you can see they converge very well, and steepest descent takes slightly more time. Remember, steepest descent follows somewhat of a zigzag direction, particularly if you are starting a little bit far away from the minimum point. It has a somewhat more complex trajectory, and Fletcher Reeves does very well. It actually is less than half of steepest descent here. Let us again review these two functions so we remember the method. So again, I had created this function here, steepest. So I have slightly cleaned up the argument list here. So only thing which goes in here is x0, tolerance, and max. And I start with x is x0. Then I have this for loop here. And within the for loop, of course, I get the gradient vector. And I said d is minus c. So all there is in the gradient descent method is d is minus c. And then I call the one-dimensional search. I create the new design here. In x is x plus the alpha into d, and then in case the gradient vector has become lower than tolerance, I break, and finally I return x and I. So that's the gradient descent function, and the Fletcher Reeves function is given here. Again, I cleaned up the argument list here, so the only thing which goes in is x0, that is the starting value, tolerance, and max. And then I once again have the for loop here. The gradient vector is defined. The time when I is 0, I said d is minus c. That is the first round, that is steepest descent method. But once you have crossed I is 0, I actually use the Fletcher Reeves search direction. So I first calculate beta, which is given here, and then I calculate d, and then I invoke the one-dimensional search using this tx, and then I update the design here. Now what I do is that I store this value of d in d old, I store the value of c in c old. Now this d old becomes dk minus 1, c old becomes ck minus 1. So that's what I'm using here. Remember, the first time this thing goes through, you simply have d is minus c. So you're not going to get into the else statement. You're going to come straight here and you are going to use that d here, and then you are going to immediately store that d in d old and c in c old. And from the next time, for example, when I is 1, 2, 3 and so on, you are going to be inside this, and each time you are going to have access to d old and c old, which is going to let you calculate this beta k and dk respectively. And of course, we have the convergence criteria that if the norm of the gradient vector is less than tall, you break. Now, of course, here we are using a new value of x. So that's what's happening here. And you can see that with this new value, I'm getting the gradient vector, and then if this is less than tall, then I'm going to break out of this particular loop. So I'll leave you with a homework problem so that you can solidify some of the concepts. So what I have done is a two-dimensional problem, so simply extend it to a three-dimensional problem. So try to write a Python code to find the minimum of the function using gradient descent and Fletcher Reeves method. So the function now is going to be x1 square plus 2x2 square plus 3x3 square plus e to the power minus x1 minus x2 minus x3. So that's going to be slightly complex function. Of course, you can figure out its actual minimum point by setting the gradient to 0 and then figuring out like I've done in tutorial 3, and then try to match the results which you get here. Now start with a point like 4 minus 3 minus 2, so it's going to take you some more time to converge, specifically with gradient descent, and then try to figure out if you have a tolerance of 0.000 or 401, what is the number of times you need to go through this for loop to converge for gradient descent and for Fletcher Reeves, and write those numbers in the comment statements of the video. So I like to see that. Please do that. Now, to conclude this particular tutorial, what we have done is we have discussed the Fletcher Reeves method. This is kind of a workhorse method in conjugate gradient search. Remember that if you have problems where you have very large number of design variables, then conjugate gradient methods are some of the best methods out there. And in those cases, certainly methods like Fletcher Reeves converge very well. The simple fact that we are slightly perturbing the search direction from steepest descent leads to much better performance of this method. So essentially this beta k dk minus 1 proposed by Fletcher and Reeves in this form is very effective as far as most problems are concerned. Of course, make it a point to look at optimization lecture 15 on conjugate gradient method. And if you are interested in the derivation of some of these formulas, I have explained them in lecture 16 and lecture 17. These methods essentially come out of the theory of quadratic forms, and if you are able to figure out that theory, then you will know how to derive the methods. But you do not need to know the derivation of the methods to use them. So again, these formulas are here and you can check it out on different functions out there.